So that's what we're showing here. We're showing models give a feel. They're a terrible way to do problems. I mean, you wouldn't want to make them do 20 of these, because this is a lousy way to do problems, right? Models are not an efficient way to solve problems. They're meant to just do one or two of them to give the feel. And then algorithms are step-by-step procedures for getting answers, right? And I talked about briefly last time, models are helpful because you know, with any concept, you want to start at the concrete level, right? Concrete, physical, like base 10 blocks and, you know, beans they can add and remove and stuff like that. And then go to pictures, which is a little more abstract. They can't touch it, but they can see it. And then step 3, of course, that's where you go to symbols, right? So on the concrete level, might be base 10 blocks. And then on the picture level, you know, pictures of base 10 blocks. And then step 3, symbols, you would actually be adding in the base 10 system with symbols, right? So there's 3 levels of understanding. Concrete, and these two are really models, aren't they? Or, well, they are models, but I don't know why I'm using a different word all of a sudden. Well, yeah, no, that's right. It's the same word. I'm getting confused. I'm confusing myself. These are models, physical and drawn, pictorial models of something, how to add, how to subtract, how to multiply, how to divide. And then with symbols, that's where you have different algorithms, different step-by-step procedures for getting answers. That's what an algorithm is. Okay, so, sorry, am I flashing off that too quick? So there's that. There's the different thing. I think I put that up last time. And, you know, models versus, both are important in math instruction. Both are important because you want to give that deep concept and you want to also have a way to get answers. That's what algorithms are for. They get you answers. So I was coming over to this problem and I was saying, we've seen a couple models at this point. We've seen, you know, like I showed you, here's a subtraction model. We've done base 10 blocks as a way to show place value models. I also showed you earlier, remember we had some arrays like that, and that showed multiplication, right? 2 times 3. Just make a big array is 6, right? The little boxes can show multiplication. On and on you go. You'll learn about those as the book will suggest different models. I just want to make sure you get the big idea that there's models and there's algorithms. There's models which show the feel. There's algorithms which get you answers. So here we are with multiplication. I'm going to show you a different algorithm. This is going to be an algorithm. In other words, it's a way to get an answer. It has nothing to do with a feel. Just another way. You know, there's other algorithms for multiplying. I gave you another algorithm for adding called scratch addition, right? Another way to add. There's lots of ways. So now I'm giving you a method for multiplying two numbers called the lattice method. They used to use it. It's actually something they used to use a long time ago. So what they would do is they would make a big array like this. And they would make it the size of whatever your numbers are. Well, they would have actually lattice paper, which had tons of lattices all over it. Ours here is going to be 2 by 3. And that's because there's a number with 3 digits and a number with 2 digits. So just like that. And then you just put one of the numbers on the top and one of them, I think. I'm a little rusty, honestly. Let me go. So one on the top. So I'll just put like the 217 on the top and the 5 on the right side. So this is going to be another way to multiply other than the standard, normal, typical way. I'm not suggesting you have kids do this. This would, just like with the scratch addition, even if you liked it or thought it was better or whatever, I wouldn't have kids do it because you'll confuse them and mess them up. That's what I did when I was first a brand new teacher 25 years ago. I thought, you know what? I was teaching different classes, and I thought, I'll show people like a couple of ways. I'll give them options. You know, when I show them a problem, I'll show them like a couple of different ways, and they can do whichever way they like best. I thought I was being so helpful. I learned after about a year that really confused everybody, that they much preferred me to just do one way and do it again and again and again and again and again, so it really sunk deep for them. So I would encourage that lesson to you that I learned. So I would not switch ways in which I teach them to add. I wouldn't, or multiply. I wouldn't ever change game plans. I'm just showing you this because I want you to have a deeper knowledge. I want you to have a knowledge that says there's more than one way to actually multiply. The way we do it is just one algorithm, and there's other ways. I want you to know the real deeper thing here. Okay, how do we do it? So I'm going to make lattices. What are lattices? They just put the diagonal lines through the boxes. It's like a lattice that, like, on some people's patio, they'll have a big lattice with a vine growing through it or something. It has those diagonals in there. Okay, so basically, what's the diagonal things for? It's for the carry. The carry is going to be right in the lattice. What do I mean? So I'm going to go box by box. So I'm going to go 7 times the top 5, and I'm going to multiply them right where they are, like a times table or something, right? I'm going to go down the 7 column, across the 5s column. They're going to meet right here, 35. 5 times 7 is 35. Just write it right there. Good so far? Hey, it's not good I put the same. Let's make it 5 and 6. I shouldn't put the same number twice. It's going to be dumb. Let's make it 56. There we go. All right, so 5 times 7 is 35. Let's keep going. 1 times 5 is just 5. Everybody see what I did there? I just took the 1 and 5, boom. They meet in this box. 1 times 5 is 5. Let's keep going. I'm going to go down the 2 and across the 5. 2 times 5 is 10. All is well so far? All I'm doing is I'm taking the number, the column, and the row, and meeting them together and multiplying. 2 times 5 is 10. That's all I'm doing. Let's go to the bottom. So 6 times 7, 42. So just write that in. 42. Next one, 1 times 6 is 6. 2 times 6 is 12. Good so far? Any questions so far? So now, where's my answer? Basically, you let the lattices guide you as to the columns. You go like this, 2. Then you go down this column, 5 and 4 and 6. So the lattices are basically having the carry effect. So that's what? 15, right? 6 and 4 is 10, and 5 is 15. So I'll do 5, and I'll carry a 1 to the next lattice diagonal. Because of 15, carry 1, bring down the 5. Then I'm going to add 1 and 3 and 5 and 2. What is that? 8, 10, 11. So it's 1. Carry the 1. How we all doing? Kaylee, you enjoying this? This making sense for you? And let me back up again. All right, I'm looking at some of your faces. So all I'm doing is I'm just going down the diagonal every time, and I'm just adding up the numbers down the diagonal. And if I need to carry, I carry to the next diagonal. It's kind of like you got to turn your head and think of these as our columns now. These are our columns, the diagonals. It handles the carry for you. So this is the 2, and then I added here, and I went just the numbers inside, not the numbers outside the box. Numbers are 6 and 4 is 10 and 15. So 5, carry the 1 to the next lattice column. And then 7, 10, 11. Add these up. Let 1, carry the 1 to the next lattice. And now I'm going down this diagonal. 1 and 1 is 2. Right? 1, 0, 1 is 2. And finally, this diagonal, 1. Okay, so what is all that? What's my answer? It's this. This is your answer. 12,152. If you multiply, that's what those numbers multiply to be. If you did it standard, it'd be the same answer. I don't think there's anything great about this. I don't see the big advantage. You'd have to have lattice paper to make it convenient anyway. I don't think there's anything great about this. I'm just showing you there's other ways to multiply. I just want you to be free from the idea that there's only one way to multiply, that the way we multiply is the only way there is, you know? You know, like, have you ever heard the statement that that if you read things outside of your culture and outside of your time period, you gain insight? Only the person that reads about books from other time periods and other cultures is therefore a little bit freed from the way of thinking of their time period and their culture. That's kind of what I'm doing for you mathematically here. I'm saying, hey, I just want to show you that there's other things, just so you're not tied in to just thinking, hey, there's only one way to multiply. That's just the magic thing. Nobody knows why it works. No. That's just one of many. It's the one we happen to use right now, but there's other ways. Adding, multiplying is a thing that can be carried out different ways. Does that make sense? Want to try one? Questions so far before I move on to one? So we're just reading about a different culture. In fact, this was a different time period. I don't know what, 1800s, 1700s, I don't remember. You can type into Google. Type in, when was lattice multiplication? You find out. Some other time period they did this. I'm just giving you perspective. How about, we'll just say this is 8b. 8b. So how about, I don't know, 23 times 468. How about that? So go ahead and make up an array, a lattice array. Put the numbers on the right and the top. You can make it 2 by 3, 3 by 2, however you want to do it. Some kind of 2 by 3 or 3 by 2 thing. Put the numbers in there and try to carry it out. I'm going to make mine 3 wide, 2 high. You can make it 3 tall, 2 wide. It doesn't matter. So 468, 23. Put in all the diagonals, There. So multiply all the numbers times the numbers. Use your calculator if you're rusty on some of these times tables. We good there so far before I dive into the lattice thing? Cut all those multiplications. Okay, so now our head cocks sideways, and we're picturing the diagonals, right? The lattices. Those are our new columns, aren't they? So I just go down the diagonal. So start right here. So this is my first diagonal. It's just 4. Then I move to the next diagonal. Add them up. 6 and 2 and 8. That's 16, right? 8, 2 is 10, 6, 16. 16. Here, let me go with a different color or something. 16. So this will be 4, 16. So 6, 1. I carried a 1 to the next diagonal. Does that make sense? So I'm looking at diagonals. So 16, I carried that 1 to the next diagonal. Right? So don't think straight up and down now. That'll get you off. You'll be like, why'd you move the 1 to the right? Don't think straight up and down or straight sideways. Think diagonal. Think diagonal. These are my columns now. So I carried the 1 to the next diagonal. So 1 and 1 is 2, and 2 is 4, and 1 is 5. 6, 7? No carry. So that was that diagonal. Now for this diagonal. 1, 1, 1. That's 10. 1, 8, 1. That's 10. 0 carry to the next diagonal. Last diagonal, 1. So here's my answer. 10,764. Is that good? Questions on that? I'm not going to do any more. I don't think there's anything great about it at all. It's just different. I wanted you to see something different for perspective. Just like reading something they did in the 1800s. It might not be better or worse, but it gives you perspective on some of the ways we're behaving in our culture. You know the time period you grow up in, you just think that's the way life is. And then you see different time periods, you're like, oh. And old time periods, don't be what do they call a chronological snob. Meaning, don't think just because it's done now, it's better or smarter. It's not necessarily. I mean, science has improved for sure, but that doesn't mean every way our culture operates is necessarily better or worse just because it's current. It gives you perspective to look at other cultures and other time periods. That's all we're doing mathematically here. All right, good. I'll move on. Maybe I'll just make up a different one. How about 23? Oh, maybe I better not. 15 into 358. I'm going to do theirs. Okay. 15 into 358. Okay, what we're doing here is we're going to show a different way to divide. So we've had a different way to add, we've had a different way to multiply. Subtraction would just be adding a negative. So really we've done adding and subtracting. And we've done multiplying, and now I'm going to show you a different way to divide. This different way to divide is by repeated subtraction. Repeated subtraction. We've talked about that briefly, right? The dividing is really repeatedly subtracting. When you're being asked, how many times does 15 go into 358? What you're really saying is, how many times can you subtract 15 out of 358? And when you're all done, how much will you have left over? Called the remainder, right? That's what you're really doing. Division is repeated subtraction. All right, so here we go. Let me encourage you on this just to make it easy. Like, don't do anything hard. Like, what I mean is when I look at 15, how many 15s go in there? I don't know. But I know, what do you know? No, yeah. I know 10 of them do. How about that? Because what happens if you multiply any number by 10? Just adds a 0 at the back, right? So 15 times 10 is 150, right? That's simple. Now, there's more than that go in there, of course. Probably a lot of you are thinking, well, can't we do 20, Ms. Taryn? That'd be 300. Yeah, but I want to keep it as simple as I possibly can. I'm just going to come over here and go, all right, I know that 10 15s. I'm going to write out the word 15 so you don't have to do that, but I'm just trying to not confuse you. So 10 15s, how much is 10 15s? Well, it's 150. Subtract, what do you got left? 208. Good so far. I've removed 10 15s from that number, 150. I've subtracted out. Now, why did I start with 10? Because it was easy. 20 would have been smarter. But, I just knew I could do that much, so it was easy, so I did it. So it doesn't matter how fast you go, how slow you go. They'll all add up. They'll all be there in the end. So now I'm looking at 208 is my current remainder. That's what's left. It's not the final remainder. That's what's remaining after I took out 10 15s, right? So now, step 2, I could take out another 10 15s. I could take out another 150. Probably more, but I don't know all that yet. I'm just going to keep it easy. Take out another 10 15s. That's another 150, isn't it? Now what do we got left? 8. Got to do some borrowing here. 2, put a 1, put a 1. 10 minus 5. 58. That's my current remainder. Now remember, I'm taking 15s out. I've taken out 10 15s, 10 more 15s. How many 15s can I take out of here? I don't know. Use your calculator. 3? I don't think 4. I think 3. 3. 15. That's 45, right? So that would be 45. So take out 45. What are you left with? 13. And you can't take any more 15s. You can't take a 15 out of 13. So that's your final remainder. How many 15s did you take out altogether? 23 15s. So I just added these up. 23 15s. So what's the answer to this problem? 23, remainder 13. We just did the long division a different way. 15 goes into 358. 15 can be taken out of 358. Same thing. 23 times. You can take 23 15s out of there, huh? And 13 remain. It's just a different way to do long division. I don't think it's any better, but it's another way to show the concept on that and to do the steps. Repeated subtraction. Does that make sense? Want to try one of those? Let's try up. How about, I don't know, well, oops, it's not working out so well. How about 26 into 789? Sort of made that up. I want to see that you can do. You can do it. Wrong? You mean for the last one?
For the remainder part.
Oh, I'll explain that in a minute. I'm glad you brought that up. We'll come back to that. Let's do this one first, and we'll come back to that. That decimal thing is not the remainder. I'll explain. Yeah, the remainder has to go over the divide. Well, I'm kind of half explaining it. I keep saying that. All right, let me go back. I like your question. I want to do it. Yeah, remember how you would actually write this answer? It's 23 and 13/15. Right? Remember, the remainder goes over the divisor. So that's another way. This is a fine way, and this is another way if you want to actually write thing. So that's what the calculator is doing. It's doing, if you take 13 on your calculator and divide by 15, I don't have my calculator with me, and I don't know what that is. It's about 0.8 something, 0.86. You see, that's what the calculator did. So it really is getting the same answer. It just doesn't show the remainder like we do. It puts it over that. That's right. And I was telling you guys about my pre-calculus students and how the real thing with the remainder and all that. Yeah, right. Trying to be real with it. Yeah, so that's what it's doing. Yeah, so on a test, yeah, you could do this with you have your calculator on the test. So you would just, on the test, you would just go 358 divided by 15. You would get the 23 part, right? So then to find the remainder, you would need to show all this, and then you would be able to find the remainder. Yeah, so let's try this one. To start taking 26s out of there. Just start with 10 of them. 10 26s, another 10 26s. So 10, and I write the word 26. You can just write 26. I just don't want to confuse people. So that'd be 260. Subtract 529. There's obviously more. I'm gonna do another 10. Another 10 26s. Another 260. What's that leave? 9. Gonna borrow here. 6. 269. I can do another 10. That's another 260. Oh, that was easy. That's the remainder, huh? So how many did we take out? 30 with 9 remainder. 30 26s came out of that number, and 9 remained. It's 30 remainder 9. Is that good? Repeated subtraction. We're showing how many times you can subtract 26 out of 789, or how many times it goes in. Same question, right? Does that make sense? Another way to long divide? Division is really repeated. See how all the operations are connected to each other? Right? Multiplying is repeated adding, right? Like we said, 3 times 7, what is that? 7 added 3 times, huh? Multiplication is repeated adding. Division is repeated subtraction. So, many of you are going to become elementary school teachers, right? That's the plan. When you're going to have some kids sitting there who are going to be future, math, science, engineer kind of people. I was one of those, and I was sitting in the class. I can't remember what grade it was, but I had heard that division could be thought of as repeated subtraction. I knew multiplication was repeated adding, and I'd heard somewhere that division was repeated subtraction. The dividing was connected to subtraction. And I remember one of the recesses saying, I'm going to stay in and figure out how division is repeated subtraction. And I fooled around on my piece of paper, and I couldn't figure it out. See, I needed someone like you guys, who was my elementary school teacher, to come up to me, someone who knows how to demonstrate that division is connected to subtraction through repeated subtraction, to come up to me and say, hey, Brett, it's recess right now. Get out of here, you weirdo. What are you doing sitting in here? Go out and kick a ball or something, would you? No, I'm kidding. But it'd be good to show me how to do this. I was interested, as weird as that may seem. I have always liked numbers and thought it was interesting that division was somehow connected to subtraction. But I wasn't very good at that. I didn't know. I needed someone who knew.